top of the mountain. From the top of the mountain.
Okay. All right. So we're talking about 5G, and this is not about 5. We shouldn't have this problem to begin with, but sorry. The three main pillars when it comes to 5G, if you look at this triangle right here, the enhanced mobile broadband, or what's called EMBB, and this is about throughputs and speed. Some of the use cases and applications that fall under this driving factor here are like streaming 8K videos, some 3D videos, and work and play in the cloud that requires a lot of speeds and throughputs. And then the second driving factor behind 5G is what's called URLLC, which is ultra reliable and low latency communication. Some of the applications that utilize this pillar or feature, they're the self-driven cars, and the robotics, for instance, surgeries, any mission critical application that depends on a low latency falls under this category. Then the last pillar is what's called MMTC, which is massive machine type communication. It's about connectivity and IoT devices and smart cities. And I'll cover this in a little bit more detail as we go on. As you know, 5G is about core and RAN. So let's take a look at the RAN part right now. The RAN is divided into units when it comes to 5G. It follows the OSI model. You have the three layers, layer 1, layer 2, and layer 3, which are the physical layer, the MAC, the RLC, PTCP, and the RRC. And to be able to utilize all the splits and all the new features that 5G is bringing, the RAN part has been divided into functional units. The first unit is called radio unit, and then it's RU, and then the DU, which is distributed unit, and then the central unit, which is CU. And there's some interfaces between these units. So the radio unit, it's the lower layer here, and it's the physical layer, which is actually the physical layer has been split, and you get the lower part of that physical layer in the RRU, in the radio unit. And then you have the upper physical unit and the MAC and RLC, which are layer 2 in the DU unit. And then you have the layer 3, which is the RRC and the PDCP in the centralized unit. And also you have the control unit and the user plane, or the control plane and user plane. The user plane, the control plane is where all the signaling takes place, and the user plane is where the data goes through. So the radio unit then, it handles the digital front end. It's like the beamforming. So it's actually, the lowest layer in the stack right here. And then we have the distributed unit, which is it is controlled by the central unit, the centralized, or the central unit, so the CU, and it takes care of the real-time L1 and L2 scheduling functionality. So it's actually a logical node within the G node B itself. Then they will have the centralized unit, which is the central unit, and it's responsible for transfer of user data, mobility, positioning, session management, and it's responsible for non-real-time layer 3 functionalities. We're doing this for a reason, and I'll explain that later on. By doing such splits and functional splits, you can actually deploy according to your use cases, and you can have different hardware depending on the splits that that you decide to have. So it could be all in one box. You can have, the whole units, the RU, DU, and CU in one box, or you can split them into 3 different boxes or 2 boxes, depending on the splits. Right. So this is another look at the splits. You can see the green is layer 1, which is the low the physical layer and the high physical layer. The yellow is layer 2, and the layer 3 is designated in red. And I'm gonna talk about this in a little bit more details. Splits are going from 1 to 8, and 8 is at the lower end of the layers. So the option 8 here, split 8, this is the CPRI. This is where the actual radio functionality is totally separated from the layers. And it's the default, the previous LTE setup. What's important here is function the split option 7, which is called 7.2 or the lo-fi. It's called lo-fi because it splits the physical layer, and the RU, the radio unit, if you can see the mouse indicator here, will have the lower physical layer here and the RF, the radio frequency hardware in one piece. This is called split 7.2. This is where the eCPRI comes into place. So this split is actually, it's the most popular split, and it's inexpensive. And one of its advantages, you get higher throughput in front haul. So this is front haul between the RU and the DU. It's called front haul, and the throughputs will be up to 100 gigabits per second. Then we have another split that's of interest right here, is called split 2, and this is F1 interface, which is called the mid haul. So we have front haul, mid haul, and then back haul back to the core. And this is it's expensive split. The RU and DU will be combined in one box, and then the CU would be separated from them. It will be at the edge, and it's a low throughput. It's like 10 gigabits per second. So it's like the split 7 is 10 times when it comes to throughput. It can handle 10 times more. And so why are we doing such splits? It is flexibility, of course, and everything is going to be virtualized, so it makes virtualization of functions much easier. Load management and flexibility, so you can actually move the functions from central to distributed to radio according to your use case here. This is another explanation, which is here, I talked about the 3 drivers or 3 pillars, EMBB and URLLC and NMTC. And if you look at this spider chart right here, the green is EMBB, and some of its features are the packet data rates are up to 20 gigabits per second. It's a green, so anything when green here pertaining to the EMBB. Area traffic capacity is 10 megabits per second per square meters here. Energy is 100 times more efficient, and the spectrum efficiency is 3 times better than LTE, and the user experience data rate is about 100 megabits per second. And the way it's deployed, the radio unit, the RRU would be at the site on a tower. And then we have the data centers here. They're divided into edge, local, or central. You will get the DU. Remember, we talked about RU, DU, and CU. DU will be closer to the edge, and then This is front haul, and then you have the mid haul between the DU and the CU. The CU would be the CU hardware and functions would be at the local data center. And then you have at the central data center, you have the actual core functionality. So these are the main features of the EMBB slice. And you know, 5G, one of important you know, fundamental that's been addressed here is called slicing, and this is just it'll give you an idea about slicing. You get an MBB slice, URLLC slice. This is again, if you remember, it's about latency, and you can see it's indicated in orange. Latency is 1 millisecond. So that's from the radio segment, and that's very low time. And then you have the mobility up to 500 kilometer per hour. And you can see the way it's deployed. You have the CU, you have the DU and RU on the tower on site, and then the CU is at the edge, and then you have the core all the way at your central data center. Then the last slice is for the mass connectivity and mass communication here. And it's all about density. You get 10 million connections per square kilometer, which is like 1 connection per square meter. And you can see you only have the radio part at the site, and then everything else will be at the central data center. Some of the main 5G RAN characteristics are, millimeter wave. According to physics, the higher the frequencies, the lower the band, the wavelengths, and that's why it's called millimeter waves. If we go into 30 gigahertz or higher, the bandwidth becomes down into the millimeters, and this will give you really high speed, but the disadvantage is only on a short ranges, and it does not penetrate buildings properly. So you need to have lots of what we call small cells. So that's the next feature, small cells. Small cells would utilize such millimeter wave technology to get you the high throughputs in the gigabits that the 5G promises. And it's low power, it's small, and but you need lots of them to get continuous coverage. About you spread the small cells 250 meters apart, and they have small antennas, and you can install them on street furnitures and poles and on traffic lights to get you that high throughputs. Another important RAN feature is the massive MIMO. The massive MIMO, you're gonna have like hundreds of antenna ports within the antenna form factor. This will increase capacity of a mobile network up to, depending on how many arrays you have, but you can have a factor of 22 or greater here. Then the last one is the beamforming. And instead of just the signal broadcasting in many directions, you actually focus on the user. The signal would be tracking the user, and that would definitely reduce interference between users. So these are the 5 main RAN characteristics. If you look at this, they call it the wedding cake because it looks like a wedding cake, and they utilize the low frequency, for instance, 700 or 600 for coverage. It's not about the throughput, but it's coverage and penetration. Then you can actually have another layer on top, which is the mid-band 3.5 gigahertz and so on. This will give you a balance between coverage and throughput. Then you have the high frequencies or the millimeter wave that's usually in urban areas, in dense areas. This will give you the actual high throughputs, but it won't penetrate, and the coverage is not that high. 5G spectrum, it's divided into two frequency ranges, FR1 and FR2. FR1 is below 6 gigahertz, and FR2 is where the millimeter wave technology comes in, and it's the 24 gigahertz and higher. You know, I listed some 5G bands that the carrier one utilizes right now, in 261 and in 41 and so on. All right, we move on to what's called Open RAN architecture. Now, as you know, we talked about the CU, RU, and DU. Now with the Open RAN, and we at Baicells, we're really very active in the Open RAN forum. Open RAN will open all the interfaces, you know, for any developers. So it's nothing, no proprietary here. You get actually DUs and CUs. You can install them on you know, industry standard, commercial, off the shelf. All the interfaces are open. And then two new layers would come into place here, what's called the non-near real-time layer with E2 interface, and then the non-real-time. So you have the near real-time and non-real-time layer with the A1 interfaces. These where you have all the applications and the KPIs and configuration of such RAN. So you have the open radio unit, open distributed unit, and then you have the centralized unit, and then you have the other two layers, the real, non-real time and real time. So that's how we moved from the standard 3GPP architecture, where it's, you know, it's not proprietary, it's a proprietary to kind of open standard technology. This is how you see it in real life. You have this is our Baicells representation of Open RAN. You have the RRU, which is the RU. If you remember, we talked about this, which is the radio head. This will be installed on the ceilings or on poles. And then you have the GPPs right here. They're standard hardware. You can actually with all the interfaces open all the way up to CU. So that's the Open RAN technology. Again, it is, you can utilize it in 3 separate pieces of hardware, or you can combine RU and DU, or DU and CU, or even you can combine all of them from hardware perspective. All right, let's talk about now core. This slide will explain to you the actual evolution from LTE to 5G, kind of more, you know, how LTE morphed into 5G. There are 3 main, if you remember, I mentioned about the user plane and the control plane. So user plane is right here, and it's called UPF. This is user plane function, and it consists of the signaling gateway and the packet gateway user planes out of the 4 LTE technology. So these 2 functions are combined to make the 5G UPF. Then AMMF, which is the access, mobility, and management function. It is the MME as we know it from LTE. Then we have the SMF, which is the session management function, and it took part of the MME and the user planes of the signaling gateways and the packet gateway. Then we have the other service functions, which is the PCF, which is for policy, and then UDM and EUF, which were the HSS function in LTE. This is another look at the core service functions. If you remember, here's the user plane right here. You know, the data flows from the UE to the RAN, which is to the base station. all the way to the UPF function, the core functionality, and all the way to the data network on the internet. And the interfaces, the RAN enters the core through N1 and N2 interfaces. That's how 5G RAN communicates with a 5G core through N, what we call N interfaces. So N1, N2 into the AMF. If you remember AMF is, it's kind of similar to the MME and LTE. Then you have the N3 interface that goes from the RAN directly into the UPF as data goes in. And these are all other functions. They call like service-based functions to serve the core functionality. So the most important ones are the EMF, AMF, SMF, and UPF. That's how the actual RAN interacts with the core. This is another representation where you have the actual G node B with the N interfaces to the 5G core and the XN interfaces between the actual G node Bs. Some of the main functions, the AMF, it's about connectivity and mobility. SMF, it's about the DHCP and IP address management, and the UPF is where the traffic aggregation take place. This is all in core related. This is another representation. You have this here is the core. You have the G node B right here. If you remember, you have N1 and N2. These interfaces go into AMF in the core. N3 is for the user plane. It connects with the UPF, and it will take it to the data network. Yeah. Okay. Now, one of the most important concepts is in 5G that actually brought all the new features from throughputs and speed and latency is the actual modulations. 5G it is adopting the scalable OFDM. Now the packets, I mean, there's some standards here and concepts that you guys need to understand. The concepts of data packets are going through frames. Each frame is 10 milliseconds, right? So each frame consists of 10 subframes, and each subframe is 1 millisecond. So this is basic information that the standards follow. Now, in LTE, and each frame, by the way, each frame consists of number of time slots. In LTE, it was fixed. Each subframe is only 2 time slots. It's fixed. You cannot change it. And each time slots is 0.5 seconds because the whole subframe is 1 milliseconds. But in 5G, that's totally different. The number of time slots in each subframe change, and it depends on what's called the carrier spacing. The carrier spacing, they're 15, 30, 60, and 120, and 240. This is also we refer to as numerology. If you can just bear with me because I'm throwing a lot of technical terms, but these are basic important functions and concepts that you guys need to understand to see. That's where the trick of the latency and throughput comes into place. Now, each slot consists of 14 symbols. For 5G and for LTE, it was fixed to 7 symbols or 6 for extended CP. So it doubled. So 5G doubled the number of symbols per time slot. And when you configure your system, all you need to do is just get the proper carrier spacing, which is called numerology, mu, to be able to control the number of slots, which indicates the bandwidth and the latency. So And another new introduction, which is something called mini slot. Mini slot, this is for 5G. It is utilizing the scalability as OFDM for the URLLC, for the low latency. So the standard slot is 14 symbols, but the mini slot can be 7, 4, or 2. So 2 symbols. I mean, it can be as low as 2 symbols. That's how you can get the low latency. Another basic fundamental here, you have the 5G resource blocks. This is the subframe right here. This is a resource block. And the smallest representation is called the resource element. So this is where the actual OFDM symbols are embedded in. And according, if you remember, I was talking about numerology 0, 1, 2, 3, 4. So this is the 5G setup from, if you need to configure your E node B, G node Bs to get the proper bandwidth. And the spacing is 15, 30, 60, 120, and 240. And then the duration, if you notice here, duration in microseconds, actually, it splits into half as you go on. So this is half of 66, half, all the way up to 4.17 microsecond for numerology number 4. This is another way of representing it, just to making it easier to understand. What I want to highlight here is the mini slot. So the mini slot, you can actually configure it to have 7, 4, or 2 symbols, depending on our use cases. This is for the latency. And you can see here, this is 1 slot, 14 symbols. Mini slot right here is only 2. So you don't have to wait until the whole time slot fills up. You know, as soon as you get these 2 symbols in here, you can actually send a message and communicate, and that's how you end up with a low latency. This is an overall frequency. Just I want to show you here the whole idea that you can see that you can have the bandwidth up to 100. You know, in LTE, you're stuck, the maximum is 20, but here, let's say in 41, you can take it depending on the actual spacing. You can actually go all the way to 100 megahertz of bandwidth. 2 ways to deploy 5G standalone. Right here, standalone is like Dish, for instance. You know, no legacy, no LTE whatsoever. You're gonna get the G node B and the core directly. So this is called standalone. But you have the NSA, which is, you know, most of our carriers here, they deploy in what's called NSA. NSA, they deploy 5G RAN, which is the G node B, and it's connected to the LTE core, the APC. No 5G core right here. So this is how they phase in their deployment and evolution. They start with the GRAN, and then they take it to the 5G core. And there are so many options to actually deploy. You move from 4G to 5G, but the famous one is what's called option 3. There are 3 configuration for option 3. If you notice 5G here, there is nothing. I mean, no other 5G is a standalone here. We have no communication with the 5G. 5G core, that's 5G core, I mean. 5G core comes in at the end. So option 3, the traffic is split between 4G and 5G at E node B, at LTE. So LTE is the master node right here. It splits the traffic between 5G and 4G. That's option 3. Option 3X, you know, the actual traffic, it's split on the EPC. So the actual EPC decides which traffic to send where, to the 5G node or the LTE node. And then we have the last option, which is option 3X. and 5G E node B or 5G node B, G node B decides the split. So the split actually of traffic is decided by 5G NGN right here. So everybody's going through option 3, and then eventually they reach to option 7, see where actually the 5G core is introduced and no more LTE EPC core. So they phase it in like this, just to protect their investments in all the RAN and core that they've invested in the past. This is, again, this is the layers. If you remember, I talked about layers. You can have the actual splitting here, where, for instance, MTC slice can be deployed over 3 regions. You know, you can actually deploy a slice into different regions depending on your case. All right, now at Baicells, we of course we are utilizing all the 5G standards and the 5G technology, and our products right now, we have products that support, when it comes to the radio part, that supports both LTE and 5G technology. In the distributed unit, because we have the RRU right here, and then we have the actual BBU. You start with the 4G BBU through 4G cards, and then once you want to move to 5G, all you need to do is just add 5G card to the x86 server, and then you will have the 5G technology. So the bandwidth can, 5G bandwidth is 100. You can utilize once you have the 5G cards in the BBU. And the EPC, it is just it's in the cloud, and it's based on x86 server. So all you need to do to upgrade, just get the 5G. There are two, different ways to upgrade, but this is the most common one, is just to get the 5G cards or 4G cards. You can actually have 4G cards at the 5G BBU as well. So it's dual hybrid technology, and it's ready. We also offer 5G test kits, standalone, non-standalone. It comes in a case. It has everything. It has the radio, RRU, the BBU, the CU, and the actual extension unit, and the core, and the CPE. It comes all in one box. It looks like this. In the lab, a lot of some of our customers have this installed in their labs to do more tests and KPIs. We have it on NSA and standalone. This is NSA non-standalone, and you can see here we have EPC. So the NSA is where actually you don't have the 5G core. You still have the NA, the EPC, but you're introducing the 5G RAM. This is a general network, mobile network for Baicells, how we connect our devices. You have the external RRU here, the outdoor RRUs. We have some with integrated radios and some with external radios. It connects to the BBU, and the BBU, if you have indoor radios right here, it connects to the BBU via what we call our hub, and then we backhaul everything into the core network. This is a closer look on the BBU. Here's the BBU and here's the RRU. You have the front haul, which is, it could be CPRI or eCPRI fiber, or we also have products with Ethernet, and it connects, the GPS connects directly to the BBU itself, and of course the antenna connects to the RRU. So this is how the actual 5G G node B look like in real life. Indoor is very interesting. It's the way it is set up. It's like access points. Here's the BBU as I talked about, and then you have the cells right here, the radio cells, and they connect to what's called an extension unit. So each extension unit can take up to 8 radios, and then you can cascade up to 4, and that will make a cell. So you can have up to 32 radios. This is for indoor configuration, up to 32 cells in one, 32 radios in one cell, and then, or you can scale it the way you want. And this BBU takes up to, handles up to 3 cells, like 3 fiber connectivities from the R hubs. This is a 5G core. It comes in it comes in standard, professional, compact. Standard is 10,000 users and about 1,000 sites. Professional, it's like 10 times that much. This is the BBU x86 server. This is where you actually have the 5G BBU cards in the accelerators and the 4G BBU cards. These connect to the radios via eCPRI or CPRI front haul. This is more specification. I don't want to go into details here, but this is a 5G. We support up to 1.5 gigabits per second on a downlink and up to 300 megabits per second on an uplink, and it takes 2 cells. We have different RRUs depending on your configuration. We have the Gamma 632. We have the Gamma 430. This is it's a dual technology, LTE and 5G, sub 6 gigahertz. The bandwidth is up to 100 megabits per up to 100 megahertz of a bandwidth because of the 5G. Spectrum is a CBRS and N41 and N78. N78 is like N41 because it includes the N41, like CBRS over 5G. So we have many different radios, indoors and outdoors. For instance, the Gamma 846, this is a 4x4 radio, 8 ports, dual technology, LTE and 5G. Band 41 and the CBRS band in LTE and in 5G, N41 and N78. They connect to the BBU. Gamma 452, also another division. We have also some indoor outdoor radios where we have the MIMO, the massive MIMO 16 by 16, 32 by 32. I talked about this, the Gamma 846 that we're currently testing, and we have some field trials on it. It is 4x4, 8 ports, 8 by 5 watts. RRU 430. Here are the extension unit and the acceleration card for 5G. This is the extension unit that connects the indoor radios, 5G radios, to the BBU. And at Baicells, we support a heterogeneous network. We can, our BBU can talk to outdoor, indoor radios, and we do offer end-to-end solutions from OMC, BOS, and the RAN parts. So that's all for me. So I'm open for questions for you guys.
Thanks, Majdi. Appreciate you taking us through that. Yeah, as Majdi said, we're open to questions. There's the chat function. There's also the Q&A. So feel free to drop any questions that you may have in that. Well, not seeing any questions come through here. we will be sending this out as a recording. You can also find it. We'll be able to find it on our YouTube channel and our website if you want to go back or direct anybody to that. If you want to stay up to date on these webinars as we go into the next year, we're going to be talking a lot about the upcoming 5G product lines, things along that nature. We'll be sending out invites as well to join our bi-weekly newsletter. It goes out every other week. It informs you of any events that we're attending, any webinars that we're doing, any ongoing product promotions that are available. So I highly encourage you to sign up for that so that we can stay up to date on everything that'll be going on here at Baicells in the next year. A question did come through. So we have, is option 3 able to use the standalone EPC?
Let me just show you the option 3 right here. Yeah. EPC, Ayan, what do you mean by EPC, standalone EPC? Option 3, just to go ahead and describe it again, the dotted lines here, they're for control, and the solid lines are for the user plane. So option 3, option 3 is you introduce the new G node B into your already existing system, into your already existing LTE network. No 5G core is implemented here. And then depending on the way, on the option, as we have option 3, 3A, and 3X, then you determine where you're actually going to split the traffic between 5G and 4G. So that's all about it. And of course, you need some upgrades or updates in the EPC to be able to handle the dual connectivity option right here. I see you agree with my explanation, Ian. Yeah. I have option 1 now, private 4G, and need a migration plan to 5G. Well, yeah, I mean, it depends how fast you want to go to 5G and the investments that's already involved and the investments that you're going to take. But usually, so option 1, you're just legacy right here. The best way to do it is go through option 3. And then from option 3, you can choose either option 5 later on or option 7. So yeah, there's so many scenarios. It depends, but the easiest way is to introduce G node B and not introduce the core, because introducing the core would complicate things at the beginning. So introduce your G node B, and you need to also update your EPC software to be able to handle that. And then you can slowly bring in the core 5G core connectivity at towards the end of your journey here. Let's see, assume that we need, all right, client does not want cloud EPC. Yeah, I mean, you don't have to have cloud EPC. Baicells, we have local EPC, and we have what called Halo B, which is actually localized with the radio itself. Or you can have cloud EPC, or you can have your own cloud EPC. So we have different ways of deploying EPC, and it's all 3GPP compliant. So you can actually connect it to any vendor's EPC. It doesn't have to be Baicells. Yeah, we do have, I'm looking at what Baicells equipment is available now that supports 5G. We do have the Gamma 846. We do, and it's on a trial basis. We have it in our labs, and we have it on our some of our customers. We have the BBU 5G. Still, it is under test, so it's not yet commercial. But we do have also the test kit that goes all the way, NSA or SA for some customers to try on the lab. I do expect full commercial. I mean, sometime during the first half of next year for all for the Open RAN and 7.2 splits and all that. Is Halo B for 5G? Is Halo B for 5G NR? No, I'm trying to understand. Is Halo B for 5G NR? Halo B is for the LTE core right now. It's not for 5G. I'm talking about the LTE, the eNode B part, because when you want to migrate, you're gonna still have eNode B and GNode B. So.
All right,
Yeah.
cool.
We have 10 more minutes, guys. Come on, more questions.
Question, can we get a copy of the presentation as well? We won't be sending out the presentation itself. We'll be sending a recording of the webinar, so that'll be able to be referenced, but the actual presentation itself will not be available.
And also, I just want to comment, I mean, LTE technology is here to stay. It's not going to disappear tomorrow. I mean, it's still growing as we go. At least it needs 5 years for it to start, to start to actually rip and replace. But that's why we have these 5G deployment options. And there's still some devices out there that don't support 5G. So you need to actually cater for LTE for some time.
Majdi, can you clarify the 5G NR radios that are shipping now and the spectrum options that Ian's asking about?
Yeah, Ian. We have, as I say, we have radios right now ready for field testing. It's not for commercial use. It should be very soon available for commercial use. But usually, our customers take the radios and the BBUs and they start testing on their own. And if they have any issues or they need support, they come to us, and we definitely support and answer all the questions. So currently we're at the field trials. The 3.3 to 3.6 gigahertz and 5 bands. Yeah, I mean, 3 that's the C band here. You're talking about. Are these 5G? You're talking about 5G bands? Yeah, that's N78. Yeah, that's N78. We do support that. N78 comes into low and high even frequency ranges. Yeah, 5.1 to 6 gigahertz. I think if I'm not mistaken, it's the N79, but I'm not sure. I come back to all this. But we do have 3.3 to 3.6, which is N78 5G band. And what's good about 5G, the technology, it has it's what's called DSS, which is dynamic spectrum sharing. That's the advantage of 5G. That 4G and 5G can use the same bands, but the only difference, 5G will give you more bandwidth. Unlicensed band for 5G to migrate and add capacity. We don't have currently 5G unlicensed bands products.
There was a question here. There's no bridging with LTE. Will this be possible with 5G?
Where?
That's under the Q&A section.
What's the, I can't see it, but what's the question again?
It is, there's no bridging with LTE. Will this be possible with 5G? Will bridging be possible with 5G is essentially the question.
Yes.
Hey, Majdi and Max, can I show a trial update?
Yes, absolutely.
Can I share the screen?
Yeah. Sure. Okay, Ronald, let me, um,
All right, Ronald, you should have presentation rights there.
yeah, I think you can control that. I for some reason I can't get out of the sharing here. Cancel. Yeah,
There you
good.
go. So to answer Chris's question, so yes, so there's 5G equipment currently out and deployed in the world, in the world, and the Baicells 5G equipment. However, it is all running on a trial basis right now. There are no commercial 5G products available yet. If that is something you'd like to learn more about, those trial 5G kits, you can reach out to our sales team here in North America, sales_NA@baicells.com, and they can get in contact with you to discuss that.
Hey, Max, are you seeing my screen?
Yep, go ahead, Ronald.
Yeah,
I
Ronald,
just want
yes.
to just update since a lot of questions about the 5G equipment availability from Baicells and their status. I just want to give you guys a quick update. We are running 5G trials, and yeah, the trials that have been involved is with the objectives uh, to have a proof of concept that the 5G is a viable alternative to fiber connectivity. And the building blocks are that we have in this trial equipment are NGCs, the core, the BBU, which is the NG RAN, and the RRU, which has both indoor and outdoor units. And the frequency band is in the sub-6 gigahertz, and including the unlicensed or lightly licensed or shared spectrums. And the performance is very positive. We have seen on the downlink more than 400 megabits per second. And on the uplink is more than 100, which is required to be competitive with the fiber communications. And these are the pictures that are taken from our trial site, the BBU, the outdoor RRU, and the indoor RRU.
Cool.
So they are getting very close to be commercialized. We're getting a lot of feedbacks, and that'll help us to make our equipment commercial ready. And that's it.
Excellent.
Thank you, Max.
Cool. Thanks, Ronald. Here, you guys can help me answer some of these more questions. Is 5G is 5G gear going to be available in 2.5 gigahertz?
There will be. Yeah, we have our products were developed for in a sub-6 gigahertz. We support the N79, which is in the 2.5 gigahertz band range.
Yeah, and N41 also, yeah.
Okay. Let's see. Another question is, in this 5G trial that you're showing here, Ronald, was that able to achieve the numbers that you showed, the 400 down and the 100 up?
Well, what's the question? The performance, the number, is it real or what?
Yeah, pretty much. Is
Yeah, it is real.
this 5G? Yeah.
Yeah, it is real. This is the real data from the field. When in the lab, the number is even higher. But this is from the trial.
So, Ron, I think as a further clarification, that specific trial that you were involved in, can you actually share? I think the real life, like for that particular scenario. Are you able to share a little bit more the actual results?
The actual results is well, are you guys looking for more details about all those numbers, the performance numbers?
Yeah, just a quick, like, high level, like, what were the test parameters that the particular client wanted to achieve?
Yes, this trial, as you can see, we mounted these radios on the rooftop, which is not very tall, if you can see in the pictures, so that quickly we get in. We lost a line of sight, but within the line of sight, we're taking a smartphones that has a 5G capabilities and walked around, and when line of sight is available, the numbers are very positive, 400 and 100 down and up. And our next step is to mount these radios at a higher buildings so that we can have a wider range of line of sight coverages, and we'll be collecting. And actually, as we speak, we're collecting more data.
Thank you.
Looks like we got another question. In the 5G trial, what was the total channel bandwidth after adding the widths of the separate carrier channel widths?
On this particular trial, we are working on a 100 megahertz channel.
Is there a way to create a hybrid network where part of the wireless network is bridged? Earlier Baicells networks could not be configured in the bridging mode, so the customer had to resort to complex tunneling schemes.
By bridging, do you mean like standalone mode?
Yeah, I think they mean by L2 bridge in L1 and Halo B. Yeah, I mean, we have this feature
Well,
already,
the
right?
trial that I'm demonstrating is a standalone architecture, and we have not developed things like Halo B in 5G yet, not yet.
Yeah.
So Eric is saying part of the customer network has to be LAN based, so the whole sector needs to be bridged. Just to help clarify his previous question.
Yeah, I think the bridging is how to say, it's a technology agnostic requirements. We support it in 4G, and we will be able to support it in 5G.
Right. Cool. Well, thank you, Majdi. Thank you, Ronald, for taking the time to answer some questions here. Like I said, we will be sending out a email following this. I'll include Majdi's and Ronald's contact information available in there if you're interested in 5G trials, where to sign up for those as well. So keep an eye out for that. If you have any further questions that were unanswered here, we can get those answers to you. Otherwise, I appreciate everybody's time here today. If you want to keep an eye out for our upcoming webinars, remember to subscribe to the bi-weekly newsletter, and we'll be sending out a link for that as well. Thank you very much, everybody. Hope you have a good rest of your day.